Okay, well, thanks for coming, everybody. So I'm Stuart Pook, I'm from Criteo, and I'm going to talk about, well, how we got to have over 300 million blocks and how we're thinking about backing up some of these blocks. Of course, I didn't do all this by myself. There's a team of 5 people that deals with the storage part of HDFS. We have a sister team called Lake Compute, which looks after the compute side, which will run the resource manager, Yarn, the different frameworks. So we deal with just the storage side, and we share making the cluster work in a low-level sort of way. So what does Criteo do? Well, we do online advertising. We follow people around on the internet, try and decide what ads they'd like to see, what products they might like to buy, with the idea of showing them an ad that interests them at the time it would interest them, at a time when they might like to click on it and maybe buy something. So the ads and even our videos are tailored to what we think the user would like to see and what the user would like to see at that particular moment. So what does that mean? In reality, we buy empty spaces on web pages. They're our publishers. And what we sell is we sell clicks to our advertisers. So there's a real-time auction every time you go to a web page. Each ad is sold in real time in an auction individually. Depending on what we know about the person looking at the web page, we will bid more or less to have the right to show the ad. If we win the bid, then we'll decide what ad to show the user. But what we sell is the fact that you click, or now even more so if you buy. So we take the risk. We participate in the ads, in the auctions. If we win the auction, we pay the publisher, but we only get money if the user clicks or buys. So what's that mean? We have lots of things happening. The HDFS is fed by Kafka. So we have up to 7 million messages a second, which come through the Kafka pipeline and pour into HDFS and getting closer to real time. So that's, I'm told, 400 billion messages a day, which is lots. So what's that mean for HDFS, which concerns me a lot more? It means that we're creating half a petabyte of files a day. A lot of that's removed, okay, because files are only kept for a certain length of time, so a file will be created on day 1 and maybe erased on day 30. So that means that we remove 410 terabytes a day, which leaves, we're adding to HDFS 90 terabytes a day. We run lots of MapReduce and Spark jobs to handle that data. What do we do precisely? Well, we do ETL, as everybody does. We do business analysis. We have lots of analysts who want to see which advertising campaigns are working, which publishers are working, which advertisers need to be throttled back or to be scaled up. We also need to do billing. We need to pay people, and we need to bill people. We need to pay for the spaces we buy. We need to bill people for the clicks we get. And most importantly, we generate the machine learning models that decide how much we should bid to buy an empty space, because we have about 70 milliseconds to decide that. So we can't do that with Hadoop, of course. So Hadoop is used to generate machine learning models which read the information we have about the user and our different publishers and advertisers to say how much we should bid for an ad and which ad to show. So these models are generated in Hadoop. What's important is that the billing is critical. At the end of the month, when it's time to do the billing cycle, Hadoop has to work. And the machine learning models are very important. Like after a couple of hours, a machine learning model will become less relevant. So they're regenerated as often as possible, sort of every hour or so. So after about 6 hours, they're not nearly as good, and after 24 hours, we're losing money. Now, I might start telling you some things you already know, but just to give a bit of background, Hadoop provides local redundancy at the storage level. We can lose a data node or two, Once Hadoop has realized that the data node is gone, it will start re-replicating the data. And so provided that you don't lose too many data nodes too quickly, your data is safe. We can lose a whole rack. We have hundreds of racks, so we can lose one of them. Once the name node has realized that the rack really has gone, it will start replicating data again. All name nodes are in pairs. There's an active and a standby, so we can lose one of the two actives, one of the name nodes, and it will fail. We can lose the active, and the standby will take over. And we have two resource managers as well, so we can lose the active one, and the standby will take over. But what we can't survive is, of course, losing a whole data center. We can't. HDFS doesn't handle 3 data nodes that fail in a short period of time. Once a data node fails, it might take an hour or so for its blocks to be replicated once again, so we have 3 copies again. And if we lose a 3rd data node during that time and we're unlucky, we can lose blocks. We can't handle 2 racks failing. And perhaps even more importantly from my point of view, we're not really protected against operator error. So we thought, well, perhaps we should back up some of these blocks. We did some calculations and realized that to back up and just to stay level with what data we want to back up, we need to back up about 1.2 petabytes a second, which is a lot. And if we have a break, if the backups stop working for a few hours or over the weekend, we want to be able to back up at 8 gigabytes a second to catch up. And of course, having backups is great, but if you want to restore because you've had a disaster, our jobs require lots of data, and so we need to be able to restore really quickly to get the cluster working again. Okay, so I think it would be really, really hard to do this in the cloud. Okay, we really need to have the backup cluster close to our data nodes, and of course, there's the compute problem. We need at least 60,000 cores to do our job, and so we'd probably have to reserve them because you can't just spin them up, with half an hour's notice, and that costs money. One of the other reasons is we don't compute in the cloud is we don't have any we have no need for elasticity. Our cluster at the moment is CPU bound and it runs at 90%, 100% all the time. Another good reason for Criteo to build data centers is that we already have data centers. To do the real-time bidding, to show the ads, that requires data centers. So we already have, I forget how many, but we're getting up towards over near 10, I think, data centers spread around the world. We have 25, 30,000 servers. So adding an Hadoop cluster or 2 adds a bit, but not that much. We already know how to do it. So what our financial people tell us is that given what we already know how to do, the fact what we already do, going in the cloud will be several times more expensive. And of course, in-house gets us exactly the network and the hardware we'd like to have. So 2 years ago, we decided to build a new data center, which is called PA4, because it's in Pantin, which is in the suburbs of Paris. We gave ourselves 9 months to do that. So we built a data center for, 5,000 machines. At the time, we had a non-blocking network. Any data node could talk to any other data node at full speed. This is no longer quite the case. I might go into that a bit later, but we're not far off it. And when we started off, we really had a low network utilization. Now we're starting to get up to 50% sometimes. So we wanted the machines to have 10 gigabit per second connection to the top of rack switches. We moved from level 2 routing to level 3 routing. We have a network topology so all the racks can talk to each other at full speed. And it uses lots and lots of electricity. So our previous data center, which is still alive, which has got 1,200 nodes, all the machines were from a single supplier. This single supplier, the machines were good, but they were starting to get a little bit expensive. So we decided to do a call for tenders. And we had 3 replies from 3 different constructors, and the machines were all rather similar. There were two different RAID cards, which was an important point, but the network cards, the CPUs were mostly the same, and there are only so many disk suppliers in the world. So we tested these machines. We had 3 racks of 10 nodes. We tested the disk bandwidth. We see if the disks worked. We did different sorts of jobs. Some jobs pushed a lot of data on the disk, so we could see whether we could saturate the disk. And other tests pushed lots of data on the network. What did we find? Well, we found, of course, that the machines were almost the same, and so they worked in a very similar way. One constructor had the bad idea of giving us 4 dead disks, and other ones failed during the test, so that one went out, and it used 20% more power. So we were lucky in that one constructor had all the bad points, so it was removed. And so the cheapest and the most dense was Huawei. And I won't go into it much in this talk, I think, but the last line is important. We bought, or they sold us, depending on how you want to look at it, this RAID card, which really didn't work. So after a couple of months, we had a running cluster with 700 or 800 nodes in it, and we had to change the RAID card without any downtime. And unfortunately, changing the RAID card meant we lost all the data on the disk. So we decommissioned a rack, let the replication finish, change the RAID card, lose all the data on that rack, bring the rack back up, rebalance back onto that rack, and we repeated that. And we managed not to have any real downtime, but certainly the users noticed that we were doing that. So don't buy cheap RAID cards is the lesson. So where we were at then and where we still are now is that we now have different types of hardware, which is good. It makes life more complicated. The hardware teams need to know how to deal with different sorts of hardware. We need different configuration because the machines are not the same. And at the beginning, one cluster would have one sort of hardware, another cluster would have another sort of hardware. Now we're starting to mix them together. So this requires us to be a little bit more intelligent. But most importantly for the hosting team, the teams that buys machines, it means they have more choice when they want to order more machines, so we can negotiate better prices and not be stuck with the same vendor. So we got all these machines, so we configured it using Chef. I haven't really mentioned it, but we use CDH5, but we don't use Cloudera Manager or anything. We use the open source Cloudera. We patch and modify our own version of CDH5. You can find it on GitHub. So you'll find quite a lot of activity where we backport patches. We do our own fixes. So all that's public. Just as an aside, it was sort of historical accident that we went with Cloudera. It's not clear that we would make the same choice today. We'd have to test. But I think the difference, given that we're just using the open source part, is so little that it's not worth us changing. So we're building Hadoop. We're testing it with 10-hour petasorts. We're tuning it because this is a big cluster. Even at the very beginning, it was 700 or 800 nodes. The name node, of course, crashed, so we had to upgrade the kernel. We decided we needed to upgrade the kernel on all the machines. We started doing that node by node, and that's just incredibly slow when you have 700 nodes. So we learned to do it rack by rack, and taking advantage of the rack level replication. Like a block is always on at least 2 different racks, so we could pull a rack down, upgrade, reboot it, and then move on to the next one. So what did we have? We had an old cluster with 1,200 nodes and a new cluster with 800, but with bigger machines, so the users loved it. They kept doing more and more things with it, and so now we were using both clusters. So we could no longer stop the old cluster, which gave us in a rather unfortunate situation in that we wanted one cluster, we wanted to have a new one to have some resiliency, and now we have to work properly. We need both clusters running, so we have 2 SPOFs rather than 1. And at this point, the old cluster was still running CDH4 and the new one was running CDH5. So we spent all this money. The users are happy. They have more resources, but the situation is in fact worse from a resiliency point of view. So what did we do? Well, we threw money at the problem. We added hundreds of new nodes to the new, which is no longer the new data center, it's the newish one. At that point, we had 1,300. And at about Q3, it became big enough to run all the jobs. And so now it's getting up to 3,000 data nodes. When you start having a cluster of that size, you can't just use any old machine to run on the name node. At the beginning in PA4, we decided all the machines would be identical, and a name node would have the same hardware as a data node. The logic being that if a name node died, well, we'd just recommission a data node to become a name node, and off we go. But it turns out that that's a bad idea, because name nodes have a very different role to play. So they need more RAM, they need more CPU, and they need SSDs rather than spinning raster. So we upgraded our name nodes. And then, of course, even that's not enough. At some point, when you want lots and lots and lots of file system objects, like that's 1,000 million, which I guess you'd call a billion. That was just too much for a name node, even if it looks like this. And buying a machine with more resources than this one starts getting very, very expensive and difficult to handle. So we did federation. We split we created 3 namespaces, we split up the hierarchy, and we told users, okay, we're going to have the root namespace, we're going to have a namespace for logs, and we're going to have a namespace for what we called loops, which are logs. So this allowed us to continue scaling, to continue adding data nodes, to continue adding blocks. You can see we haven't quite been able to balance it yet. The 2 smaller namespaces with 200 million and 150 million objects at a reasonable size. The root namespace is still too big, so we're going to have to split it again. And unfortunately, this is not completely invisible to the users because they can no longer move files atomically from one directory to another. So in the beginning, we had one namespace, so a user's jobs would create a file in one directory, and when it was finished, would move it into another directory. In some cases, this is no longer possible, so you can't. You keep this in mind. If you're starting to get more and more blocks and you're thinking of federation, think where you're going to need to cut the space in 2 and check that you don't have users wanting to do atomic moves between the 2 spaces. So we've now got our 3-headed namespace. So what do we have? So now we're feeling a little bit better now. We still have a SPOF, but we only have one of them. All jobs are now running on the new cluster. The old cluster still has some files it's used for just backups. We're not really equipped to run jobs on it. So we have some backups, but we don't have any compute redundancy. So I guess you can imagine what one does in this situation. You can ask yourself, even in this case, is our data safe? Well, what's in common now is us, the operators, and the code in Git, which is used to manage both these clusters. If I'm writing a command to do something to remove a temporary directory which is too big on all the machines, and I put a space in the wrong place in the command line, instead of removing the temporary directory, I'll just remove all the files. And it's also the same chef code which runs on both clusters. So it's easy to imagine making a mistake and just erasing everything. So what do we want to do? We decided, okay, let's do some backups on a different technology. So you've already seen the figures that we were given to be able to do backups. When we did the proof of concept, we did it with 10 petabytes on 100 machines. These days, our users will probably tell us that they want to back up 20 petabytes. Anyway, so the test was with 10. So we tested Ceph, OpenIO, and Mapper. The first 2 are open source solutions, which we really loved, but neither of them was sufficiently stable to be able to just install it and run it. So we decided to give money to Mapper to use their technology to provide us a backup cluster that's on a different technology. So we're still negotiating with them about how much money we're going to give them, and once that's done,